The morning of September 14th, 1943, northwest of Cape Ortegal, Spain, Oberleutnant See Heinrich Müller stood in the cramped control room of U-402, studying the depth gauge as it climbed past 60 meters. His boat had been submerged for 13 hours, evading a persistent Sunderland flying boat that had forced them down at dawn. The batteries showed 31% capacity. The air tasted metallic, thick with carbon dioxide that made every breath an effort. They needed to surface. They needed to run the diesels. They had no choice. Müller gave the order at 09:15 hours. U-402 broke through the grey Atlantic swells, seawater cascading off her deck as the conning tower emerged into weak morning sunlight. The lookouts scrambled topside, scanning the horizon through salt-crusted binoculars. Empty ocean, no aircraft, no ships, just the endless rolling waves that had been their battlefield for 6 weeks. The diesel engines coughed to life with their familiar reassuring rumble. Müller allowed himself a moment of relief. They had evaded successfully. They would charge batteries for 2 hours, then submerge again before resuming their patrol toward convoy routes west of Ireland. Standard procedure. Textbook evasion. 11 minutes later, the same Sunderland appeared from behind a cloud bank at 800 feet, diving directly toward them with bomb bay doors already open. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Müller's scream for crash dive coincided with the first depth charge hitting the water. The lookouts threw themselves through the hatch. Green water poured into the conning tower as they sealed it. The vents opened with their characteristic metallic shriek. U-402 tilted forward desperately, trying to reach safety depth before the charges detonated. The explosions arrived in perfect pattern. 4 depth charges bracketing the submarine's length. The detonations lifted the stern, buckled plates in the engine room, shattered instruments throughout the boat. In the suffocating darkness, as emergency lighting flickered red, Müller asked himself the question that haunted every U-boat commander in the autumn of 1943. How did they find us again? How did they know exactly where we would surface? The answer floated directly above them. A small paper cylinder, 3 feet long and 5 inches in diameter, bobbing in the Atlantic swell, its hydrophone suspended 24 feet below the surface, listening to every sound U-402 made, transmitting acoustic data via radio to the circling Sunderland. A weapon so simple, so effective, that German naval intelligence would never identify it. Not in 1943, not in 1944, not until after Germany surrendered in May 1945. The Allies called it a Sonobuoy. The Germans never called it anything because they never knew it existed. To understand how this weapon changed submarine warfare, we must first understand what German submariners believed about Allied detection capabilities in 1943. The intelligence briefings at U-boat headquarters in Lorient, France, painted a clear picture of the threats German submarines faced. Allied aircraft carried sophisticated radar systems capable of detecting surfaced U-boats at ranges exceeding 20 miles. The British had reportedly perfected infrared detection, sensing the heat signature of diesel exhaust against cold ocean water. Some reports suggested the Allies had deployed magnetic anomaly detectors that could sense steel hulls through seawater itself. These were the threats that dominated every tactical discussion, every training session, every nervous conversation in officers' messes from Norway to France. German submariners knew about radar because they experienced it directly. Their METOX receivers could detect radar emissions, providing precious minutes of warning before aircraft arrived. When the Allies switched to centimetric radar in early 1943, rendering METOX useless, German engineers scrambled to develop the Naxos detector to counter the new threat. The technological race was visible, measurable, understood. Radar transmitted electromagnetic waves through the air. Detect those waves, and you could evade the aircraft that carried them. It was physics German engineers comprehended and could counter with electronic warfare techniques developed throughout the war. What they couldn't comprehend was how Allied aircraft found U-boats that had been submerged for hours. Boats that hadn't transmitted on radio. boats that showed no heat signature, boats that hadn't broken the surface where radar could detect them. How did patrol aircraft arrive precisely over submarines that had been underwater since dawn, forcing them to remain submerged until batteries died and they had no choice but to surface directly into carefully prepared ambushes? German intelligence developed increasingly elaborate theories to explain the inexplicable. Perhaps the British had perfected magnetic detection, sensing steel hulls through water, with equipment more sensitive than existing technology suggested possible. Perhaps the Allies had deployed vast networks of underwater listening stations connected by cable to shore facilities, creating an acoustic surveillance grid across the Atlantic. Perhaps, as some desperate reports from beleaguered U-boat commanders suggested, the Allies had recruited dolphins or trained seals to locate submarines using natural sonar abilities. The explanations grew increasingly fantastic because the reality was too simple to imagine, too primitive, too effective. Aircraft were dropping buoys that listened. That was all, just listening. The development of the Sonobuoy represented a convergence of technologies so straightforward that its effectiveness seemed almost unfair to German submariners, who never understood what hunted them. In May 1941, British physicist Patrick Maynard Stewart Blackett, head of the Admiralty Committee for Anti-Submarine Measures, proposed a concept elegant in its simplicity: an expendable acoustic sensor that aircraft could deploy over suspected submarine locations. The idea required no exotic physics. Submarines made noise. Water conducted sound efficiently over long distances. Radio could transmit that acoustic information to aircraft. 3 proven technologies combined into a weapon system that would help win the Battle of the Atlantic. The Americans developed the same concept almost simultaneously through independent research. In June 1941, the Office of Scientific Research and Development contracted with Radio Corporation of America to develop a radio sonobuoy for deployment from surface ships, trailing behind convoys to detect following U-boats. The initial design proved disappointing during sea trials conducted in September 1941 at Barnegat Bay, New Jersey. The acoustic range was too limited, detecting submarines only at distances under 1 mile. The electrical components proved too fragile for rough sea conditions. The Navy initially rejected the project, prioritizing other anti-submarine research with more immediate promise. But scientists at Columbia University's Underwater Sound Laboratory at Fort Trumbull, New London, Connecticut, refused to abandon the concept. They recognized that the fundamental principles were sound. The execution simply needed refinement. They modified the design for air deployment rather than ship deployment, eliminating the need for convoy vessels to stop and deploy sensors. They simplified the electronics, using components already in mass production for other military applications. They selected materials that weren't critical to other war production, ensuring the project wouldn't compete for scarce resources. The redesigned Sonobuoy used paper tubes, coated for waterproofing, as the outer casing. 1/4-inch thick paper, hardly the material one would expect in a weapon system that would revolutionize naval warfare. But the coating kept it watertight for several hours, long enough to complete its tactical mission before sinking. Inside, 5 vacuum tubes, the same type used in ordinary radios, powered a half-watt transmitter. Flashlight batteries, available in enormous quantities, provided electrical power for 4 to 6 hours of operation. On March 7, 1942, Navy blimp K5 cruised over waters south of New London, Connecticut, monitoring 2 RCA sonobuoys, while submarine S-20 ran submerged below at various depths and speeds. The hydrophones detected the submarine's propeller noise at distances up to 3 nautical miles. The radio reception aboard K5 remained clear at ranges up to 5 miles. The test lasted 3 hours and proved the concept absolutely. Russell L. Mason, the civilian engineer aboard K5 that afternoon, had just witnessed the first time in history that an aircraft detected a fully submerged submarine through acoustics alone. He would spend the next 35 years refining sonobuoy technology, but in March 1942, all he knew was that he had watched something revolutionary, a weapon that turned the ocean itself into a surveillance system. By June 1942, the AN, CRT-1, became the first operational Sonobuoy approved for combat deployment. The first air-droppable version weighed 15 pounds and measured 3 feet long by 5 inches in diameter, a size that would become standardized as A size for Sonobuoys. This standardization allowed any Allied aircraft equipped with appropriate launching tubes to deploy the sensors, from Navy blimps to Army bombers to RAF flying boats. The outer cylinder construction from quarter-inch thick paper tube would have shocked German engineers accustomed to over-engineering their equipment. German military equipment emphasized durability, precision manufacturing, sophisticated components. American engineers emphasized practicality, mass production, adequate performance at minimum cost. The Sonobuoy epitomized this philosophical difference. It didn't need to last for years. It needed to work for a few hours, then sink, leaving no trace for the enemy to recover and analyze. Inside the paper cylinder, 5 vacuum tubes powered a half-watt radio transmitter tuned to one of 6 FM frequencies, each corresponding to a color for easy identification: purple, orange, blue, red, yellow, green. The color coding allowed aircraft operators to monitor multiple Sonobuoys simultaneously by simply noting which colored frequency was receiving the strongest signal. The hydrophone, constructed of ruggedized nickel magnetostriction material, deployed to a depth of 24 feet on a weighted line. This depth provided optimal acoustic reception in typical Atlantic sea conditions, deep enough to avoid surface wave noise, but shallow enough to detect submarines operating at periscope depth or preparing to surface. The system's genius lay in operational simplicity that required minimal training. An aircraft operator could drop multiple Sonobuoys in a pattern, then tune the ARR3 receiver manually, using the color-coded tuning window to compare acoustic intensity from each buoy. By noting which buoy received the loudest signal, the operator could triangulate the submarine's approximate position without complex calculations or sophisticated equipment. The acoustic signatures proved distinctive enough that trained operators could differentiate between submarine propeller noise and ambient ocean sounds, between German diesels and Allied vessels, sometimes even between different U-boat classes based on propeller cavitation patterns and machinery vibration frequencies. On July 25, 1942, U.S. Army Air Force's B-18 bomber dropped the first operational Sonobuoy from an aircraft during an actual anti-submarine patrol off the American East Coast. The technology transitioned from experimental concept to operational weapon in less than 5 months, a development cycle that would be remarkable even with modern project management techniques. By August 1942, Colonel Dolan of the Sea Search Group operating from Langley Field, Virginia, was expending Sonobuoys in offshore operations against U-boats patrolling American coastal waters. The word expending reflected the weapon's disposable nature. Unlike radar sets or sonar equipment that required maintenance and repair, Sonobuoys were used once and abandoned. The economics favored mass deployment. Better to drop 100 Sonobuoys that detected one submarine than to save resources while submarines escaped. The Germans noticed something had changed almost immediately, but they couldn't identify what. In the summer of 1942, U-boat captains began reporting inexplicable encounters that defied tactical logic and challenged their understanding of Allied capabilities. "I don't know how it happened, Herr Admiral," one commander told Admiral Karl Dönitz during mandatory debriefing after returning from patrol. "We were submerged at 80 meters, no transmissions, complete silence. Suddenly a Liberator came through thick cloud cover straight toward us and dropped depth charges. They couldn't possibly have seen us through the clouds. Our METOX showed no radar emissions." Another commander reported surfacing at night in heavy weather, conditions that should have made visual detection impossible and radar detection difficult. "We were surfacing at normal speed when suddenly we heard aircraft engines. They were directly overhead before we could complete crash dive procedures. The sea state was force 6 with low clouds and rain squalls. Visual detection was impossible. Radar should have been ineffective in those conditions." The pattern repeated across the Atlantic throughout late 1942 and into 1943. U-boats approaching convoys at night found destroyers detaching from screening positions to intercept them before they could reach attack positions, despite maintaining absolute radio silence that should have prevented direction finding. Submarines that crash-dived and evaded to new positions miles away discovered aircraft waiting for them when they surfaced hours later, as if the enemy had predicted their exact movements. German naval intelligence analysed every encounter report, searching for common factors that might explain Allied detection capabilities. The conclusion seemed obvious and fit existing threat models. The Allies had deployed new radar systems, possibly operating on wavelengths German detectors couldn't sense. This explanation matched German understanding of Allied technological development and suggested countermeasures German engineers could develop. The alternative explanation, that Allied aircraft were simply dropping listening devices into the ocean and waiting for submarines to make noise, seemed too primitive to consider seriously. Too simple, too crude. Too unlike the sophisticated electronic warfare that dominated naval operations. German military culture valued technical sophistication and engineering excellence. The concept that a paper tube filled with vacuum tubes and batteries could defeat their submarines seemed absurd. Admiral Karl Dönitz, commander of the U-boat force, addressed the crisis in a conference with Adolf Hitler in May 1943. His analysis revealed both the sophistication of German tactical thinking and its fundamental blindness to the actual threat they faced. The substantial increase in enemy air forces is the cause of the present crisis in submarine warfare, Dönitz explained to Hitler and the assembled military leadership. However, submarine crisis would not have occurred solely as a result of increased enemy aircraft numbers. The determining factor is a new location device, evidently also used by surface vessels, by means of which planes are in a position to locate submarines when the ceiling is low, visibility poor, or at night. Without this device, the planes would be unable to locate submarines at night or in heavy seas. Every word of Dönitz's assessment was factually correct. Every conclusion was strategically wrong. A new location device existed. Aircraft were using it with devastating effectiveness. Surface vessels were coordinating with aircraft using information from this device. But it wasn't the advanced radar system Dönitz imagined. It was something far more insidious because it was undetectable. A weapon that turned the submarine's own machinery against it. That exploited the fundamental requirements of underwater operations. Propellers must turn to move the boat. Diesels must run to charge. Batteries. Compressed air must flow through ballast tanks to surface and dive. Every necessary sound became a beacon for Allied aircraft circling overhead, listening through hydrophones dropped hours earlier. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By December 1943, the United States Navy had ordered 59,700 CRT-1 Sonobuoys. These devices, manufactured with 6 radio frequency channels, were being distributed to anti-submarine squadrons across the Atlantic theatre at a rate exceeding 5,000 per month. The production numbers alone should have alerted German intelligence to the scale of deployment. 59,000 units represented far more than a technological experiment. It represented a systematic campaign to blanket the Atlantic with acoustic sensors that could detect submerged submarines at ranges German commanders believed impossible. But the Germans never captured an intact sonobuoy. They never recovered one from the ocean. They never examined its internal components or understood its operating principles. The paper casing, designed to be waterproof for only a few hours, ensured the devices sank after completing their tactical mission. The electronics, damaged by seawater intrusion and pressure, became unrecognizable wreckage on the ocean floor, indistinguishable from ordinary debris. German naval intelligence possessed fragments of evidence, acoustic contacts that appeared moments after aircraft passed overhead, patterns suggesting that aircraft could predict submarine movements with uncanny accuracy. But they never assembled these fragments into recognition of the actual threat. The psychological barrier proved insurmountable. The weapon was too simple, too crude, too unlike German engineering philosophy to be taken seriously as an explanation for their mounting losses. The psychological impact on U-boat crews became measurable in ways German Naval Command found increasingly difficult to ignore. In early 1943, before Sonobuoys reached widespread deployment across the Atlantic, the average U-boat patrol lasted 65 days. Crews returned exhausted but confident, reporting successful attacks and narrow escapes that reinforced their sense of tactical superiority and professional competence. By summer 1943, patrol durations had shortened to 47 days on average. Not because boats were achieving their missions faster, but because commanders were aborting patrols after experiencing the paranoia of being hunted by an enemy that seemed to possess supernatural knowledge of their positions. The psychological burden of fighting an enemy who appeared to know submarine locations at all times proved as damaging as actual combat losses. Korvettenkapitän Peter Kremer, commander of U-333, documented this psychological erosion in his war diary with unusual candor. "We crash-dive at the sound of every aircraft engine, real or imagined," he wrote in August 1943. "The men jump at shadows." Yesterday, the hydrophone operator reported propeller noises that turned out to be a school of fish. The day before, we dove because someone thought they heard aircraft, but it was wind whistling through the periscope housing. We cannot continue this way. Every noise becomes a threat. Every moment submerged feels like being buried alive, waiting for depth charges we cannot evade. Every moment on the surface feels like standing in an execution yard, waiting for the shot we won't hear until too late. Kremer's diary entry reflected experiences shared across the U-boat force in the second half of 1943. German submarine warfare had transformed from aggressive hunting to desperate survival, from confident attacks on Allied convoys to paranoid evasion of Allied hunters. The psychological transformation was as complete as it was devastating to German morale. The British conducted parallel Sonobuoy operations under the codename High T, deploying their own version from RAF Coastal Command aircraft beginning in July 1942. No. 2 10 Squadron became the first operational unit, flying short Sunderland flying boats equipped with British-designed Sonobuoys over the Bay of Biscay. The British design philosophy differed slightly from American doctrine. Where American procedures emphasized rapid deployment and triangulation using multiple buoys to locate submarines quickly, British operators focused on extended monitoring of specific areas. The Sunderland's remarkable endurance, capable of patrol missions lasting 13 hours, allowed them to maintain acoustic surveillance for extended periods, waiting patiently for U-boats transiting between French bases and Atlantic patrol areas. Flight Lieutenant James Thompson flew one of those early high-T missions over the Bay of Biscay in August 1942. His after-action report, preserved in RAF archives at Kew, provides insight into the operational reality of Sonobuoy warfare from the aircrew perspective. Deployed 6 Sonobuoys in line across suspected transit route at 0700 hours, Thompson wrote in the clinical language required for official reports. Maintained patrol altitude of 800 feet, monitoring all 6 frequencies in rotation. At 11:20 hours, buoy number 4, orange frequency, registered strong machinery noise, consistent with diesel engines running at moderate power. Altered course to investigate while continuing acoustic monitoring. At 11:47 hours, achieved visual contact with U-boat on surface, approximate bearing matching acoustic contact. Attacked with depth charges. Results assessed as probable kill confirmed by oil slick and debris. The clinical language concealed the revolution Thompson had witnessed. He had detected a submarine running submerged using only acoustic sensors, tracked it for 27 minutes, while it remained completely unaware of observation, positioned his aircraft for optimal attack, and achieved visual contact only seconds before attacking. The U-boat crew would have attributed the attack to unlucky visual sighting or possible radar detection during a brief surface period. They would never have imagined an aircraft had been listening to their engines through hydrophones suspended in the water miles away, tracking their every movement. The technical specifications of the AN, CRT-1, reveal precisely why German detection proved impossible despite their sophisticated electronic warfare capabilities. The hydrophone operated passively, emitting no signal that submarine sensors could detect. Unlike active sonar systems used by surface warships, which transmitted acoustic pulses through water and listened for echoes that betrayed range and bearing, the Sonobuoy simply listened to the ambient noise environment created by submarine operations. A U-boat's hydrophone operators, highly trained to detect active sonar pings from escort vessels or propeller noises from approaching surface ships, had no way to sense a passive listening device floating on the surface above them. The detection methods they understood involved either visual observation, electromagnetic radiation like radar, or active acoustic pulses. A device that merely listened was outside their threat model entirely. The radio transmitter operated on FM frequencies between 36 and 50 MHz, well outside the range of German radio direction-finding equipment designed to intercept naval communications in much lower frequency bands. German radio operators monitored frequencies used for Allied tactical communications, typically below 20 MHz. Even if a U-boat's radio operator happened to scan across one of the Sonobuoy frequencies during routine electronic surveillance, they would hear only the modulated audio signal representing underwater sounds transmitted in real time to the aircraft. Without context or understanding of what they were hearing, the signal would be meaningless, dismissed as atmospheric noise or unidentified Allied communications. The operational doctrine that evolved around Sonobuoy deployment exploited German tactical patterns with ruthless efficiency. U-boat commanders, trained in aggressive warfare philosophy, emphasizing decisive engagement, followed predictable behaviors when under threat. When detected by radar, they crash-dived immediately to evade the attacking aircraft. When harassed repeatedly by aircraft, they moved to new patrol areas under cover of darkness. When batteries depleted to dangerous levels, they surfaced in locations they calculated to be beyond aircraft range, based on known Allied air bases and typical patrol radii. Allied anti-submarine forces learned these patterns through systematic analysis of U-boat behavior and developed counter-tactics specifically designed to exploit German predictability. An aircraft detecting a U-boat with radar would mark the dive location precisely using navigation equipment, deploy a pattern of sonobuoys around the area in a circle or line formation, then appear to leave the area by flying away beyond visual and audible range. The submarine, believing it had successfully evaded detection, would eventually need to surface to recharge batteries and refresh air for the crew. The moment its diesel engines started, the moment its propellers began turning, the moment any machinery operated, the Sonobuoys registered the acoustic signature. The aircraft, which had been orbiting beyond detection range while monitoring Sonobuoy frequencies, would return with devastating precision, often achieving complete surprise because the U-boat crew believed themselves safe after hours of apparent isolation. Oberleutnant See Heinrich Müller experienced this tactic in September 1943 while commanding U-737. His patrol report, recovered from German naval archives after the war, documents an encounter that perfectly illustrates the psychological warfare dimension of Sonobuoy operations that German submariners never understood. At 03:15 hours, radar detector indicated aircraft approach. Müller wrote in the standardized format required for all patrol reports. Executed emergency dive to 90 meters. Maintained silent running procedures for 2 hours. Hydrophone reported no surface vessels in area. Sea state calm. Conditions favorable for acoustic detection of any nearby threats. At 05:30 hours, with batteries at 32% capacity, surfaced to run diesels and recharge. Within 4 minutes of surfacing, aircraft appeared from cloud cover at low altitude and attacked immediately. Sustained minor damage from near-miss depth charge. Successfully crash-dived to 120 meters. Cannot explain how. The aircraft located us with such precision. Radar detector gave no warning of approach. Hydrophone detected no surface vessels that could have marked our position. Weather conditions poor with low clouds and rain squalls, making visual detection nearly impossible at the range from which attack was launched. Müller's report concluded with a statement that appeared in dozens of U-boat patrol reports from this period. Crew morale severely affected, men asking questions I cannot answer. The questions Müller couldn't answer would haunt U-boat operations for the remainder of the war. How did aircraft know exactly where to search when submarines surfaced? How did they arrive so quickly, often within minutes of surfacing, as if they had been waiting? How did they maintain contact even when submarines evaded to new positions miles from their last known location? The psychological burden of fighting an enemy, who seemed to possess inexplicable knowledge of submarine locations, transformed the weird nature of U-boat warfare fundamentally. In 1942, German submariners called themselves Grey Wolves, hunters who struck from the depths with deadly precision, terrorizing Allied convoys and sinking merchant vessels faster than they could be replaced. By late 1943, they had become prey, constantly hunted, always vulnerable, never safe, even in the vast emptiness of the Atlantic Ocean. The transformation wasn't merely tactical, it was existential, affecting how submariners viewed their profession and their chances of survival. The acoustic signature of a Type 7C U-boat, the most common German submarine design with over 700 built, became as distinctive to trained Allied operators as a fingerprint is to a detective. The diesel engines produced characteristic low-frequency rumble between 20 and 100 Hz, a deep throbbing that propagated efficiently through seawater. The electric motors used for submerged operations generated higher frequency noise from brush contact with the commutator and armature rotation, typically between 200 and 800 Hz. Most distinctively, the propellers created cavitation bubbles, tiny voids in the water caused by rapidly spinning blades, creating low-pressure regions where water literally boiled at ambient temperature. These cavitation bubbles collapsed with sharp acoustic pops that carried for miles underwater, creating a characteristic signature that experienced operators could identify instantly. American and British acoustic analysts developed detailed classification systems for these sounds during intensive training programs. Facilities at Norfolk, Virginia, and Londonderry, Northern Ireland, taught sonobuoy operators to distinguish between different submarine classes based on machinery signatures, to identify whether a boat was running on diesel or electric power based on frequency analysis, to estimate speed and depth based on propeller rotation rates, and machinery noise levels. The level of acoustic intelligence detail became extraordinary by 1944. Some experienced operators claimed they could identify individual U-boats by subtle variations in their acoustic signatures, like recognizing a person by their voice. A particular diesel engine with a worn bearing produced a slightly different frequency spectrum than an identical engine in perfect condition. A propeller with minor blade damage created asymmetric cavitation patterns that trained ears could detect. Whether these claims of individual identification were accurate or reflected operator overconfidence, the systematic acoustic intelligence collection represented a dimension of anti-submarine warfare that Germans never suspected existed. German acoustic research concentrated almost entirely on offensive applications, developing acoustic torpedoes like the T-5 König that homed on propeller noise of Allied escort vessels. The concept that Allies might be using similar acoustic principles defensively to hunt submarines rather than sink surface ships apparently never gained serious traction in German naval research programs. This blindness persisted despite mounting evidence that something fundamental had changed in Allied anti-submarine capabilities. In May 1943, Admiral Dönitz made the unprecedented decision to withdraw U-boats from North Atlantic convoy routes after losing 41 submarines in a single month. 41 boats lost in 31 days. The losses were mathematically unsustainable. At that rate, the entire operational U-boat force would be destroyed within 6 months. The tactical situation had reversed completely from the early war years. In 1940 and 1941, U-boats attacked convoys with devastating effectiveness, sinking merchant ships faster than Allied shipyards could replace them, threatening to starve Britain into surrender. By May 1943, convoys hunted U-boats. The prey had become predators. The hunters had become hunted. Dönitz attributed the crisis to Allied air power, to improved radar that German detectors couldn't sense, to the closing of the mid-Atlantic air gap, where U-boats had once operated beyond the range of land-based aircraft. All these factors contributed genuinely to German losses and featured prominently in German tactical analysis. But the Sonobuoy represented something more insidious than any of these recognized threats, a weapon that made the ocean itself hostile territory, that transformed every square mile of Atlantic water into a potential listening post. That gave aircraft the ability to detect submarines in conditions where radar failed completely and visual observation was impossible. Weather that should have protected U-boats from air attack instead became irrelevant when aircraft could track them acoustically regardless of visibility or sea state. The scale of Sonobuoy deployment in the final 2 years of the war reached levels that would have shocked German intelligence had they possessed any knowledge of the program. Between October 1942 and May 1945, Allied forces dropped approximately 150,000 Sonobuoys into the Atlantic Ocean. 150,000 acoustic sensors deployed from aircraft in systematic patterns that created overlapping coverage across vast areas of ocean. Some Sonobuoys were deployed in systematic barrier patterns, creating acoustic fences across known U-boat transit routes that submarines could not cross without detection. Others were dropped opportunistically, marking areas where submarines had been detected or were suspected to operate based on intelligence analysis. Still others were used in hunter-killer operations where surface ships and aircraft coordinated to trap U-boats in progressively smaller areas, using sonobuoys to maintain continuous contact even when submarines dove to extreme depths, attempting to break contact. The tactical employment of sonobuoys evolved throughout 1944 and 1945 into increasingly sophisticated operational patterns that German commanders never understood. The barrier pattern, developed by U.S. Navy patrol squadrons operating from bases in Iceland and Newfoundland, involved deploying lines of sonobuoys across known U-boat transit routes between Norwegian bases and Atlantic patrol areas. Aircraft would lay a pattern of 15 to 20 buoys in a line spanning 20 to 30 miles, creating an acoustic fence. The buoys were spaced close enough that a submarine's acoustic signature would be detected by at least 2 and usually 3 or 4 sensors, allowing accurate position determination through triangulation. Once a sonobuoy registered contact, additional aircraft would converge on the area, deploying more buoys to track the submarine's movements and maintain contact until surface ships arrived to prosecute the attack with depth, charges and hedgehog mortars. Oberleutnant Hans-Georg Hess, commanding U-995, encountered one of these acoustic barriers in February 1944 while transiting from Norway to patrol areas southwest of Ireland. His experience, documented in both his patrol report and post-war interrogation by Allied intelligence officers, illustrates how sonobuoy operations appeared from the German perspective, completely inexplicable, yet terrifyingly effective. We were proceeding submerged at 4 knots, running on electric motors to minimize acoustic signature as ordered by headquarters directives, Hess reported. Depth 120 meters. No radar emissions detected by Naxos equipment. No surface contacts on hydrophone. Sea state calm. Excellent conditions for remaining undetected according to all tactical doctrine. At 1400 hours, hydrophone operator reported distant aircraft sounds, bearing indeterminate. We reduced speed to 2 knots and maintained. Course, standard evasion procedure. At 1430 hours, first depth charges, approximate range 2,000 meters. We altered course, 90 degrees as trained, more depth charges at 1500 hours, closer this time, perhaps 800 meters. We increased speed to 6 knots and altered course again. Aircraft seemed to anticipate our movements. Depth charges fell consistently within 500 meters of our position, despite our evasive maneuvers, and despite maintaining continuous submerged operations. We cannot explain this capability. It is as if the enemy can see through the ocean itself, tracking our movements regardless of depth or speed changes. What Hess couldn't see were the 8 sonobuoys deployed in a line across his transit route, their hydrophones detecting the electric motors and propeller noise of U-995 as it attempted to evade. What he didn't know was that each course change, each speed adjustment, was registered by the acoustic sensors and relayed via radio to 3 circling aircraft that took turns attacking, while the others monitored sonobuoy frequencies and coordinated their approaches. The submarine was never beyond observation. Every sound it made, every mechanical necessity of underwater operations, betrayed its position to enemies Hess believed were somehow guessing his location through inexplicable technology he couldn't comprehend or counter. The cumulative psychological effect on U-boat crews manifested in ways that German naval medicine struggled to address adequately. By late 1944, the average patrol report included references to crew anxiety, sleep disturbances, and what German psychiatrists began documenting as Horchfurcht, listening fear, a condition where hydrophone operators became convinced they could hear Allied detection devices that didn't actually exist in the forms they imagined. Men reported hearing mechanical clicks, electronic hums, rhythmic patterns in ocean noise that they interpreted as enemy sensors, actively tracking their boat. Some hydrophone operators refused to remove their headphones even during off-watch periods, convinced that constant vigilance might detect the mysterious devices hunting them. Others experienced auditory hallucinations, hearing attack patterns in random ocean noise, reporting torpedo launches that never occurred, detecting surface vessels that didn't exist. The paranoia had basis in reality. Something was hunting them with precision that seemed supernatural, but the specific mechanisms they imagined, underwater robotic sentinels, cable networks linking shore stations across the Atlantic, magnetic sensors detecting steel hulls from impossible distances, bore little resemblance to the simple paper cylinders bobbing on the surface above them, listening passively with hydrophones and transmitting via radio to aircraft they never detected approaching. The German response to unexplained aircraft attacks concentrated enormous resources on countermeasures that addressed the wrong threat entirely. Engineers developed the Naxos radar detector to replace the obsolete METOX system that couldn't detect centimetric radar. They designed coating materials, including experimental rubber compounds, intended to absorb radar waves and reduce the submarine's radar cross-section, making U-boats harder to detect with airborne radar sets. They experimented with infrared-absorbing paints after becoming convinced the British had perfected infrared detection capable of sensing diesel exhaust heat signatures at night. Millions of Reichsmarks, thousands of man-hours, entire research programs addressed a threat model that was partially correct, acknowledging that Allied detection had improved dramatically, but fundamentally incomplete because it never identified the actual primary threat. The one German countermeasure that might have detected Sonobuoys never received sufficient development priority to reach operational deployment. In 1943, German naval engineers proposed equipping U-boats with receivers capable of scanning the FM radio spectrum used by Allied aircraft for tactical communications. The technology existed. Germany possessed excellent radio direction finding equipment and sophisticated receivers capable of monitoring a wide range of frequencies. But the project received low priority in resource allocation because German intelligence assessed, incorrectly, that Allied aircraft were using radar, not radio-transmitted acoustic data, to locate submarines. The receivers that could have detected sonobuoy transmissions, allowing U-boat commanders to know when acoustic sensors were operating in their vicinity, remained engineering prototypes in laboratories, while U-boats continued dying from attacks they couldn't understand or predict. The operational records preserved in Allied naval archives reveal the devastating effectiveness of coordinated sonobuoy operations when surface ships and aircraft worked together using acoustic intelligence. In March 1944, aircraft from escort carrier USS Guadalcanal, operating southwest of the Azores, deployed sonobuoys to locate U-544 after the submarine had evaded an initial depth charge attack by crash diving and running silent at 150 meters depth. The aircraft maintained acoustic contact for 7 hours, while destroyer escorts USS Pope, USS Flaherty, USS Pillsbury, and USS Chatelaine converged on the area from distances exceeding 40 miles. The surface ships, guided by continuous position updates radioed from aircraft monitoring Sonobuoy frequencies, pursued U-544 through multiple evasion attempts that would have succeeded against conventional detection methods. The submarine altered course 8 times, changed depth 5 times, released bold decoys, metal foil strips designed to create false sonar echoes and confuse Allied sonar operators. Released Pillenwerfer, chemical canisters that created bubble clouds to mask acoustic signatures. None of the countermeasures worked against passive acoustic detection from above. The Sonobuoys simply listened. Every evasion attempt created noise. Every noise was detected, analyzed, and transmitted to the hunting forces. U-544 finally surfaced after 23 hours of continuous pursuit, its batteries exhausted to 7% capacity, its crew unable to continue submerged operations. The submarine's capture, along with its code books and Enigma machine, represented one of the most significant intelligence coups of the Battle of the Atlantic. The operation succeeded primarily because Sonobuoys provided continuous tracking that prevented the submarine from escaping into the vast Atlantic, where it could have evaded surface ships that lacked continuous contact. Oberleutnant Harold Lang, the commander of U-544, described his experience during post-capture interrogation by U.S. Navy intelligence officers. His statement, preserved in declassified records at the National Archives, reveals the German perspective on capabilities they never understood. "We could not understand how the destroyers maintained contact," Lange explained to his interrogators. "We changed depth continuously. We changed course every 30 minutes, following evasion doctrine exactly as trained. We ran silent, securing all non-essential machinery to minimize noise signature. We released bold decoys that should have confused their sonar. Nothing worked. They knew where we were at every moment, maintaining contact despite all our efforts. Some of my officers believed the Americans had developed acoustic torpedoes that tracked submarines, explaining the persistent contact. Others thought you had placed detection devices on the seabed, creating a network that tracked our movements. I had no explanation to give them. I still have no explanation. It was like being hunted by ghosts who could see through steel and water, who knew our thoughts before we acted." The profound irony of Lange's statement lies in its essential accuracy, despite complete misunderstanding of the mechanism. He was being hunted by devices that effectively saw through water, not with light or radar or magnetic fields, but with sound. The oldest form of remote sensing known to humanity, employed systematically with 20th century electronics and tactical coordination. The sophistication lay not in exotic physics or advanced technology, but in systematic application of basic acoustic principles, combined with recognition that submarines must make noise to operate, and that water conducts sound efficiently enough to detect that noise at tactically useful ranges. By early 1945, Sonobuoy technology had advanced beyond the simple omnidirectional hydrophones of the AN CRT-1. Development of the AN CRT-4 directional Sonobuoy began in February 1943, though the system didn't reach operational testing until early 1945, too late to affect the European War significantly. This larger, more sophisticated device measured 6 1/4 inches in diameter and 52 1/2 inches in length, weighing 30 pounds compared to the 15-pound CRT-1. It featured a rotating directional hydrophone assembly, turned at 3 to 5 rotations per minute by a gravity-powered motor using a 500-foot-long fishing line as the mechanical linkage. The directional capability would have allowed single buoys to provide accurate bearing information without requiring triangulation from multiple sensors, dramatically improving tactical efficiency. But the war in Europe ended in May 1945 before the AN CRT-4 could prove its operational value in combat. The Germans never encountered it, never captured examples, never learned of its existence or capabilities. The Germans never learned about Sonobuoys at all, not during the war. Not through captured equipment, despite recovering numerous pieces of Allied military hardware from shot-down aircraft and sunken ships, not from interrogation of Allied personnel, despite capturing thousands of British and American aircrew throughout the war, not from intelligence analysis, despite German naval intelligence employing hundreds of analysts specifically tasked with understanding Allied anti-submarine capabilities. The security surrounding Sonobuoy technology remained intact until well after Germany's surrender in May 1945. When German naval officers were finally briefed on Allied anti-submarine sensor capabilities during post-war technical exchanges organized by occupying forces, their reactions ranged from disbelief to bitter resignation. The simplicity of the concept shocked them. Paper tubes filled with vacuum tubes and batteries dropped from aircraft, floating on the surface, listening. That was all. No exotic physics, no advanced materials, no breakthrough in electromagnetic theory. Just systematic application of basic acoustic principles that German engineers understood perfectly well, but never considered applying in exactly this manner for exactly this purpose. The elegance of the execution impressed them despite their defeat. The Sonobuoy represented everything German military engineering was not: simple rather than sophisticated, disposable rather than durable, adequate rather than perfect, yet devastatingly effective precisely because it matched operational requirements perfectly while remaining undetectable to enemy countermeasures. Admiral Dönitz, in his post-war memoirs written during imprisonment at Spandau, reflected on the technological surprise that contributed to Germany's defeat in the Battle of the Atlantic. His assessment reveals both intellectual honesty about German failures and lingering bitterness about Allied advantages. "We knew the Allies had radar," Dönitz wrote. "We developed detectors and countermeasures, though always trailing their advances by months. We knew they had improved sonar on their escort vessels. We developed tactics to evade it, remaining at depths where sonar performance degraded. We knew they had broken some of our codes. We implemented new encryption procedures and changed communication protocols regularly. But we never knew about the listening devices they dropped from aircraft, small buoys that floated on the surface, listening to our engines, our propellers, every sound our boats made, transmitting that information to aircraft circling beyond our detection range. We couldn't defend against a threat we didn't know existed. We couldn't develop countermeasures for a weapon we never identified. Perhaps that is the most bitter lesson of all. We were defeated not by superior force alone, though Allied industrial capacity vastly exceeded ours. We were defeated not by better tactics alone, though Allied anti-submarine doctrine evolved effectively. We were defeated by superior knowledge of our own ignorance. They understood what we didn't know. They exploited that ignorance systematically, and we never discovered the deception until after surrender, when it no longer mattered. The final statistics of the Battle of the Atlantic reveal the magnitude of Germany's failure to understand Allied detection capabilities and the catastrophic consequences of that failure. Between 1939 and 1945, Germany commissioned 1,154 U-boats of all types. 783 were lost in combat operations, representing a casualty rate of 68%. Approximately 30,000 German submariners died, 3/4 of the total submarine force of 40,000 men who served. These losses occurred despite German submarines achieving significant successes, sinking approximately 3,000 Allied merchant ships, totaling 14.5 million gross tons, and 175 Allied warships. The exchange rate favoured the Allies overwhelmingly, not because German submarines weren't effective weapons, quite the contrary, but because Allied detection and tracking capabilities rendered them vulnerable to a degree that German naval command never fully grasped until after the war ended. The Sonobuoy represented only one component of the comprehensive Allied anti-submarine warfare system that defeated the U-boat threat. Improved radar, operating on centimetric wavelengths that German detectors couldn't sense until very late in the war. High-frequency direction finding, allowing shore stations and escort vessels to triangulate on U-boat radio transmissions. Ultra-intelligence from decrypted German communications, providing advance warning of U-boat positions and intentions. escort carriers providing continuous air cover for convoys, very long-range patrol aircraft closing the mid-Atlantic air gap where U-boats had once operated beyond, land-based aircraft range. All these capabilities contributed to Allied victory in the Atlantic, but the Sonobuoy possessed unique characteristics that made it particularly devastating to German operations. It worked when radar failed in heavy weather. It detected submarines that maintained radio silence, providing no signals for direction-finding equipment. It tracked boats that had dove too deep for magnetic anomaly detectors. It turned every Allied aircraft into a potential submarine hunter, even in sea states and weather conditions that rendered visual observation completely impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The legacy of World War II Sonobuoy development extended far beyond immediate tactical applications in the Atlantic, shaping anti-submarine warfare doctrine for decades. The AN/CRT-1 and its successors established fundamental principles of airborne, acoustic detection that remained relevant through the Cold War confrontation with Soviet submarines and into the 21st century. Modern Sonobuoys, vastly more sophisticated than their World War II predecessors, incorporating digital signal processing, automated classification algorithms, secure data links, and advanced hydrophone arrays, continue serving as primary sensors for maritime patrol aircraft and anti-submarine helicopters worldwide. The basic concept, a disposable acoustic sensor deployed from aircraft and transmitting data via radio link, proved so effective that subsequent decades of technological advancement merely refined the execution rather than replacing the fundamental approach. The German submariners who survived the war carried with them memories of being hunted by an enemy whose capabilities they never fully understood during combat operations. In veteran associations, in oral histories recorded decades later, in memoirs published long after the conflict ended, former U-boat crews described the paranoia of submerged operations in 1944 and 45 with remarkable consistency. The conviction that Allied forces possessed some form of supernatural knowledge, the helplessness of being attacked by aircraft that appeared from nowhere, struck with devastating accuracy, then departed, leaving crews wondering how detection had occurred. The psychological burden of fighting an enemy who seemed to know submarine locations at all times, who anticipated evasive maneuvers, who waited patiently for inevitable surfacing. They were correct in their assessment. The Allies did possess knowledge that seemed supernatural from the German perspective, appearing to track submarines through methods that defied German understanding of physics and detection technology. But the knowledge wasn't supernatural. It was acoustic. It was systematic. It was effective. And it remained secret long enough to help win the Battle of the Atlantic, ensuring that sea lanes between America and Britain remained open for the massive build-up of forces that would eventually liberate Europe from Nazi occupation. The story of the Sonobuoy and German ignorance of its existence stands as testament to the decisive importance of technological surprise in warfare. Not necessarily the most advanced technology, not the most powerful weapons in absolute terms, but the unexpected application of proven principles in ways that enemy intelligence cannot anticipate, cannot detect, and cannot effectively counter. The Germans never knew that paper tubes filled with batteries and vacuum tubes, dropped from aircraft and floating on Atlantic swells, were listening to every sound their submarines made. Hydrophones suspended 24 feet below the surface, detecting machinery noise and propeller cavitation. Radio transmitters broadcasting that acoustic intelligence to aircraft circling beyond detection range. Simpler technology, elegant execution, devastating effectiveness. That ignorance cost them control of the Atlantic. That ignorance cost them their submarine force, with casualty rates exceeding any other branch of German military service. That ignorance cost them any realistic chance of starving Britain into surrender or preventing the Allied build-up for the invasion of Normandy. And ultimately, that ignorance contributed to their defeat in World War II. The Sonobuoy wasn't the weapon that won the war by itself. No single weapon system determined the outcome of a conflict as vast and complex as World War II. But in the specific domain of anti-submarine warfare in the Atlantic Ocean, the Sonobuoys represented a capability gap that Germany never closed because they never identified the gap existed. They fought against threats they understood, radar and sonar and code breaking, while the actual threat that hunted them most effectively remained invisible to their intelligence analysis until after surrender made that knowledge irrelevant. The lesson resonates beyond World War II into contemporary strategic thinking. In any conflict, the unknown threats pose greater danger than the known ones. The capabilities an enemy possesses, but you don't recognize, create vulnerabilities you cannot address. The Germans knew they were losing the Battle of the Atlantic by mid-1943. They understood that Allied detection had improved dramatically. They developed countermeasures, tactics, and technology to address the threats they had identified. But they never identified the primary threat. They never captured a sonobuoy. They never recognized what was hunting them. And that ignorance, maintained from July 1942 until May 1945, helped ensure that when Allied forces landed on the beaches of Normandy on June 6, 1944, German U-boats could not interdict the invasion fleet, could not sink the thousands of vessels carrying men and equipment to establish the Western Front, could not prevent the liberation of Europe, all because paper tubes with hydrophones floated on the Atlantic, listening. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.